So the material is prepared based on Python 3, and the environment we're going to use is Jupyter Notebook. So you can clone our repository to get all the material. And before we trigger the Jupyter Notebook, we can install all the necessary packages so that we can start. Okay, all right. So if you turn on Jupyter Notebook, right, you can can you see the notebook? How should I turn it? Okay, can you see the notebook playing? Okay. So in the first part of the hands-on tutorial, right, we're going to train magic factorization algorithms. In this particular case, we're going to change probabilistic magic factorization model, and the data set that we're going to use is movie length 1 million. Yeah, so with Jupyter Notebook, then you just need to click on the cell of the code and press Shift Enter to execute the code. So the first part, you can import all the necessary package and the utils that you need to run the notebook. So as a summary, right, a typical magic factorization recommendation system has two phases. The first phase is a learning phase, in which you derive a d-dimensional vector for each user and for each item. And the user item interaction is modeled usually as through the inner product kernel, meaning the prediction for the preference of a particular U to a particular item I is defined through the inner product between the user vector and item vectors. So after the learning phase, right, you have a vector representation for the user and a vector representation for the item. And what you need to do at the retrieval phase is to compute the preference score for each user, and then you rank these scores to finally get the top K for recommendation. So this is a diagram to illustrate the two phases of a recommender system. The upper part is the learning phase, and the lower part is a retrieval phase. So if you execute so if you look at the part about probabilistics magic factorization, right? So there is the objective function, the error function, in which I try to minimize the.
So in case you don't have it set up and you have difficulty looking at this, we do invite you just to move up a little bit, because I think what we are showing the content inside the notebook. If you have it set up on your laptop and you can see it, I think that's fine. But if you would like to move up, please do. There are a lot of space in front.
Maybe I can still zoom up a little bit. How about this? Okay, so the objective of PMF model is to minimize this error function, which is minimizing the error between the actual rating score and the predicted score. And for the data set that we're going to play with is MovieLens 1 million data set, which contains 1 million ratings from 6,000 users on 4,000 movies. So I already put the data set in the data folder. So if you already close the repository, you can already have the rating data set for MovieLens. So in order to train and evaluate the model, right, first you need to split the data into training and testing. So for simplicity, I only split them into training set and testing set. I will not have the validation test. But so in this case, right, the ratio that we use to split the training and testing is 70-30. So we hide 30% of the ratings for evaluation purpose, and we keep 70% for training the PMF algorithms. So the part that you actually train the PMF algorithms is in this cell. So if you execute this cell, right, and you can observe that the training root mean square error of on both the training data and the testing data are reducing. So here I only run with 100 iterations. The number of features is only 100. So you can see that the error is reducing on both training and testing, but it stopped at the equals 100. Okay, so we're gonna save the model as well as the training and testing data for future use. Okay, so let's say that after you train the model, right, and save the model as well as training and testing data, right, we can do some experiment to see what, let's say when we vary the number of items, then what is the cost of the retrieval phase. So in this part, right, I'm going to just hide the items and then review them over time. So if you execute the code, right, you can see that when we increase the number of items from 1 to 4,000, and the vertical line is actually plotting the required computation time to do the inner product computation. So you can see that as the number of items increase, then the computation time also increase, and the shape of the curve is actually like a linear form. So it means that as the number of items increase, right, the computation time required also increase, and it increase linearly with the number of items, which we can see from the analysis, right? The time complexity of linear scanning solution is actually at the cost of the number of items times the number of dimensions. Anybody has any question? All right. If not, then we experiment with another. Okay, so this is when we vary the number of features. So we also expect that as the number of dimensions of the features, as the number of features increase, then also so as the computation time required to compute the inner product. So you can see that it's actually showing more like a linear line as the number of dimensions increase from 1 to 100. So these two experiments actually show that if you do linear scanning for the retrieval problem, then the computation time required is actually linearly increased with the number of items as well as the number of features. So after this, right, we can see that the observation is actually matched with the theoretical analysis on the complexity of linear scanning solution. Okay, so having understood the cost of linear scanning, so we're going to move on to the second part, in which we try to scale the retrieval process using locality sensitive hasing. So here inside, right, we already provide the library for locality sensitive hasing. So if you look at the code, then locality sensitive hasing index actually has few features. The first feature is that which hash family that you want to use. Either is L2 locality sensitive hasing or cosine locality sensitive hasing. And you can also define the number of hash functions that you want to draw. How many hash tables that you want to use for retrieval purpose. And so in order to use the locality sensitive hasing, first you need to index your data, which can be done through this index function. So once you have the index, the built index, you can do the query, which the input is a query, and the matrix. The matrix is like whether you use equidistant or cosine similarities. And this query function will return you the tokay, which you can define through this max results. So let's say you want to retrieve top 10 recommendation, then you just need to pass 10 to max results parameter here. So in the lower part, right, you can see the definition of two different localities hashing family. The first family is for equidistant or L2 distance. And the second part is the cosine hash function. So what you do is that you first create the hash function, right? And then after you create the hash function, you build the index, you index your data, and once you have the build index, then you can do the query using the build index. So that's pretty much the structure of how you design locality sensitive hasing and how you can use it to do recommendation retrieval. So any questions about LSS? Okay, if not, then I go back to the notebook, right? So remember that in the first part we trained PMF with movie lens 1 million dataset, and we already saved the model as well as the training and testing data. So here in this second notebook, we just reload the model as well as the training and testing data. So first we measure the performance of linear scanning solution. We define the number of recommendations that we want to get. In this case is top 10. We want to have 10 recommendations. So the metrics that we measure the performance is precision and recall, and you can evaluate the performance through this evaluate tokay function. And you can see that the precision and recall of PMF model on movie lens 1 million dataset is about 6% and 2% for 6% for precision and around 2% for recall value. So this is the result you get if you perform linear scanning. So how about the result if you use locality sensitive hashing? So this diagram is basically a summary of how you can use locality sensitive hashing to do the recommendation retrieval. So first you define the hash functions, right? And then you build the index of the data vectors. So the result is going to be a hash table in which in each hash cell contains the item that has similar hash code in the first column. So let's say you have 4,000 items, right? Then each item will belong to one of the cells in this hash table. So by the time you have the user vector, then you hash the user vector to get the hash code, right? So let's say the hash code of the user is 11011, and you look for all the items in this hash cell, right? And all of these items in this hash cell will become the candidates for top K that can be recommended to either you. However, this is only just the candidate set. So there could be more candidates than the actual number of recommendations that you want to receive. In this case, is 10. So after you get the candidate set, you actually need to perform the exact inner product computation again to actually filter out the top K largest inner product items. So this is a result of the top K recommendation that generated for the ELU. So in order to testify the performance of retrieval using locality sensitive hashing, we report three values here. The first value is relative precision. It is defined as a precision of locality sensitive hashing divided by the precision value of linear scanning. So the same definition for recall. We just see how much accuracy of the linear scanning solution is preserved by locality sensitive hashing. So the third value is what I define as touch. It's basically the number of items that you need to do exact computation. So for linear scanning, right, you need to do the exact computation with all the items in the data set. But for locality sensitive hashing, because of this hash table, right, you only need to touch a subset of the items, and this touch value is going to see actually how much, how many of them you actually need to touch, and you should expect that this number of investigated items is smaller than the number of items that you have in the data set. So here, so in the presentation, we just see that you can actually do some vector transformation to make sure that the accuracy of locality sensitive hashing is high. So here we define two experiments. The first experiment is that we do the LSS but without any vector transformation. So in this case, we just we don't do anything. We don't do any transformation on the user vector as well as item vectors. So I define them as the same queries and same data variables. So it's basically don't do anything, don't do any transformation for the user vector and query vectors. So you see, by just padding 1 0 value to the end of the user vector and item vectors, you still get the same maximum inner product search problem. And the second experiment is that we actually apply the Xbox transformation. So what is the Xbox transformation? So the Xbox transformation, right? You first transform the user vectors by augmenting them into one more higher dimensional space. So this is the original item vectors, and the augment, and you add this value to the end of the item vectors. in which M is the maximum magnitude of all the item vectors. So after this transformation, what you get is that you get all the items with the same magnitude, and they will have all the same values, which is M in this case. For the query, for the user vector, you just simply peg the 0 value to the end of that vectors. So with this transformation, right, then you convert from maximum inner product search to maximum cosine similarity search. So I define the transform vector as the Xbox data and the Xbox queries. So if we don't do any transformation, then we have same queries, same data. If we apply Xbox, then we have Xbox data and Xbox queries. So in order to compare between the two representation, right, the one without transformation and the one with transformation, we gonna try with different number of hash tables and different number of hash function for locality sensitive hashing. So you can see that the reported result, right? The first row is the result without any transformation, and the second row is with Xbox transformation. With the same number of hash table with the same number of bits, you can see the relative precision and relative recall for the model that employ the Xbox transformation is actually higher than the model without employing the Xbox transformation. So if you look at the touch value, right? So the LSS that does the model that doesn't employ Xbox transformation actually touch less number of items. In this case, 34% of number of items, as compared to the model that employ Xbox, which will touch nearly 50%. So that means that if you employ the Xbox transformation, then the LSS scheme will touch more items as compared to if you don't employ Xbox transformation, and it results in higher accuracy, higher precision and recall as compared to the model that don't employ Xbox transformation. And this observation holds true if you try with different number of hash table and different number of hash functions. So what is the key takeaway from this is that you can employ this vector transformation after training your algorithms, so that the result of the recommendation using locality sensitive hashing can still guarantee high quality. Alright, so any questions for the second part? So you can see that actually using vector transformation can help you achieve higher accuracy of recommendation, whereas you can still guarantee that the speed of the retrieval is fast because you only touch a fraction of the number of items. Alright. Okay, so if you go back to the repository, right, then there's a part 3 in which we talk about indexable representation. So in this particular experiment, right, we make use of a library which is Connect. So Connect is a recommendation library that's developed by our group. So if you look up on the on Google, right, you can find the website that introduce about. Maybe that we open. Okay, so Connect is a Python-based recommender system library. So now we currently provide a framework so that any researcher or practitioner can employ your own recommendation algorithms using this framework. We also provide some existing state-of-the-art recommendation models, as well as evaluation strategies and different way to play with your data. And in the future, we're going to provide the pre-change model in which you can actually bootstrap your recommender system using some existing state-of-the-art recommendation algorithms. Just to take this opportunity to let you guys know that there is a very easy and convenient Python-based library that you can use to build your recommendation system. Okay, so for the experiment for indexable representation, then we basically will we talk about two models. The first model is Bayesian personalized ranking, which is BPR in short. So in BPR, right, we actually try to maximize the difference between the preferred items to the less preferred item. In this case, the preference score is still the inner product between the user vector and the item vectors. But for IBPR, then what we want to achieve is that for the more preferred item, we want the angular distance between the user vectors and the item vectors of the more preferred item vectors will be smaller than the angular distance between the user vector and the less preferred items. And that's actually can be achieved using this probability, the inequalities. So in Connect, we already provide the implementation, the code for both BPR and IBPR. So the details of the implementation, the parameters you can find and you can find in the documentation of the library. We also maintain a public GitHub repository so that later on anyone can clone and contribute your own algorithms to Connect. I will briefly just explain what going on in this notebook. So first of all, right, we use the same data set in which is movieland 1 million, and we just train BPR model using the implementation in Connect. So we already provide some pre-change model in which we save as BPR.model. So you can execute the code to see the performance in terms of precision and recall of the pre-change model. So if you have time, you can fine-tune the hyperparameters like the learning rate or the batch size so that the model will achieve higher precision or recall. And you can do the same for indexable BPR. We also provide a pre-trained model, and you can execute the code to see the performance of both linear scanning as well as the performance using locality sensitive hasing. And we should expect to see that because of the natively indexable properties of IBPR, we should see that accuracy, the performance of IBPR after indexing is going to be better than that of Bayesian personalized ranking. That's pretty much it. All the materials are provided on the GitHub repository. You can clone the repository and play with the code a little bit. You can change the value of the hyperparameter to see how the performance of the model change, and you can also play with the number of hash table or the number of hash function that you want to use to build your index. So that's pretty much about the hands-on session. So the last part, Hadi is going to talk about the discrete representation learning, in which they try to learn the user and the items in terms of they try to represent user items in terms of binary codes instead of real value vectors. So that's going to help in terms of speeding up the inner product computation, because operation on binary values is faster than operation like multiplication or addition on the real value vectors. So that's why discrete representation is also one of the approach that you can use to speed up the retrieval process. Okay, so with that.